Production quality through the roof here. There it went. Okay, good. Now it's decided that it's gonna go. Yay! Oh hey, hello Space Pad. How's it going? Go check this place out, dude. We're doing a little bit of a, I think it's media Q&A is what they're calling it. Look at the lighting in here. There's actually lighting. Look, you can see it back behind me. There's like actual camera crews and stuff like that. Yeah. Hi. How's it going? We are going to stand by for this. This is supposed to go live at about, I think 1 p.m. So in about 10 minutes here, and they said it's supposed to last for about 90 minutes. I don't know if we could like get some links or something like that to it, but I'll read chat. I'm not sure exactly. We can move out of the way. I'm not sure exactly what I'm going to do here. I might just like sneakily put it down or something like that. Live for you. Is it looking, C-Cuff, is it okay? Here, I'll point at the ceiling like that so we don't get the lights in it. Oh, wow. Good job, Cameron. I guess that's fine. Whatever. How do I look? Do I look pretty? Are my glasses straight? That's fine. All right, cool. I do not understand why the chat doesn't automatically scroll. That actually really gets on my nerves with this Bitstream app. Stream emote, chat emotes. What's that? Use chat emotes. Nice. It's fine. Okay, C-Cuff. Good deal, dude. Good. I am not going to be talking very much at all here. I'm not going to be talking. I'm not sure exactly what I think about this because they are going to be streaming it. So probably the right thing to do is to get the actual link to NASATV. If somebody could get that and put it in chat, that's where the real quality sort of broadcast is going to be. This is just like the behind the scenes. Like, look, check it out. I'm sitting in the like kind of press conference area over here. Just load the pop-out chat from Twitch. I could actually bring my laptop up. I just don't know that I'm going to do that right now. I think I got it fixed. Anyways, we might need some people, like some mods or just some people to be explaining. I'm not going to be talking very much here because it's actually, they're going to be doing a real sort of press conference. So I'll sit here. And if there's a question or something like that, like if you see them actually ask for questions and you have a question for one of the people, you can type it in a chat and I will not say anything to you. I'll type to you. But if you want to ask a question, like tell me, I'll ask questions and stuff like that. There you go. Thanks, Mutter. Appreciate it, dude. Anyways, that's kind of the plan for now. We'll see how it goes. I haven't done this before. I don't know. We'll see. Hey, Peanut Butter. How's it going, dude? How you doing? Anyways, if you're just coming in, we're standing by for the press briefing or something like that. Of course, they didn't tell us what we're standing by for. We're just standing by for it. So you can see I'm actually in the NASATV sort of room right now. And stuff. So go watch that link over there. Also, I think they're going to do a Facebook Live thing too. All right. I think we just all got quiet for no reason because it's still like 6 minutes before they go. Just like everybody start to get quiet. Good times. Hey, Pood, thanks for the 7 months, dude. Appreciate it. What's on board science briefing? Okay.
How's everybody doing?
We're doing good.
So for the social folks that's on, just so you know, if you want to share it, this is going to be broadcast on NASATV starting at 1 o'clock, so that's in about 6 minutes, 5 minutes. And so as a result of that, if you want to share it with folks, it's at www.nasa.gov/NASATV. And so we'll be on there, and we'll be taking questions using the hashtag AskNASA on social media. So
there you go.
If you want to tell your followers, they're welcome to ask questions. Sarah over there will be running through all the questions and everything, and we'll be going through that in addition to the ones that you guys have here in the room. Don't be shy. These are the experts to talk to and definitely get to know all about the experiments that are going up and so on. So. Yeah, nasa.gov/NASATV.
What's the hashtag for asking questions?
Ask NASA.
NASA, that's easy.
try to make it foolproof. Other questions, comments, concerns?
Yeah. Unless you have a chair off to the side.
All right, you guys are thinking science now, right? You got your questions going. We gave you a quick preview this morning. What's on board? You've been thinking about it a few hours. It's like lightning round. Who's got the first question here? Somebody got it ready? No?
Here, the planets in space. You guys work Joya. We're doing the Fairchild project, and we've done 4 trials in the past 2 years.
I just saw the team talk on that.
Yeah.
For the science.
My students love it. So actually this last trial, we're done with Fairchild and we did a Fairchild trial. So, yeah, it's really GA
Which is because,
All right. I think we got it taken care of. There we go. So again, y'all, we're standing by. It's like 3 minutes. We'll get some links to the actual conference thing so you guys can get the actual video from the real cameras that are back here and over there and basically everywhere. But that's kind of the deal for now.
So just like most live TV audiences, remember clapping, hooting and hollering is good for good stuff. You know, be animated, be loud, let the world know you're watching.
We got you.
Oh, better. All right.
Pre-recorded
I
studio
know we're in
audience.
like
Thanks,
that
Marty.
government issue, like
Thanks,
TV
Steve.
auditorium, it's kind of stuffy and stiff. You know, don't let it get to you. It's gonna be good.
the more you clap, the more I dance. So
Okay. Is there like an applause light somewhere?
If you will, don't forget to turn your ringers off.
Are you with Casey?
Yeah, let me make sure my ringer's always off.
Do you do story time? Are you in charge of the story time from space?
Not like literally.
Oh, but like your people?
I'm reading. Cheer now, yeah.
I
Cheer now.
submitted
I'll just
the
behind.
word.
Y'all can cheer too. Y'all can also cheer.
That'd be awesome.
I'm trying to be like kind of like low pro here, like kind of leaving the camera down, like not doing anything. It's no big deal. Of course, it gives me a really unflattering angle. What you gonna do? Oh, dude, thanks, Hydra. Thanks.
Yes. 1 minute.
1 minute.
That's when we start petering and
yes, sir.
30 seconds.
We're gonna try to actually do this.
Scoochy, unless
Sorry,
you want to put
sorry.
your arm around
I'm getting cozy.
That's not the marks. I got it. Good. Okay, get in between the marks for the rest of you who are coming. Not all. Read between. Don't block the next.
10 seconds.
10 seconds, folks.
Good afternoon. Thank you for joining us live from NASA's Kennedy Space Center in Florida. I'm Cheryl Warren in the Office of Communications. We're here live with an audience who is excited to see a launch. Am I right? We're here today for What's on Board to discuss some of the science that's headed to the International Space Station. Launch is targeted for April 18th at 11:11 a.m. Eastern. from Cape Canaveral Air Force Station in Florida. Today, we'll have a number of guests that come up and talk to you about the exciting science that we're sending to the station. I will ask questions from the audience as well as online. So if you're following us on social media, please use the hashtag AskNASA. Our first guests today are Dr. Tara Ruttley and Dr. Mike Roberts. Tara?
Great. So thanks, everyone. I'm not kidding when I say it's really fun to be here at the Kennedy Space Center. You sound like you're already pumped up. Got me pumped up, too. It seems like you've seen some really interesting things today so far, right? Yeah. This is a really great place to be right before a launch. You get to see some of the science processing facilities. I'm from Houston, Texas, at the Johnson Space Center. I work in the Space Station Science Office. I kind of woo, yeah. Yes. So I have the coolest job, I think, here.
Second coolest.
We'll talk about that. Because I get to see all the science that comes across and heads for the space station, including the National Lab science that Mike's going to talk a little bit about. So I've gotten a chance to speak to some of the scientists who are here today, whose payloads are going up on this next launch. And they're ready to talk to you, so it's going to be an exciting hour. To give you just an overview of Space Station, you all know, I think, for the most part, that it is a laboratory. It's a research laboratory in space. Now's the time to use this laboratory as a way to test out some of the systems and do some research involved in how we go and explore beyond the Earth orbit. There's lots of human physiology we need to understand. There's lots of technology development. There's food production that you're going to hear about. Things that we need to take the time now to use the laboratory to move forward. But I mean, it's also a platform by which it gives us a unique environment to try new things we haven't done before, to do new studies that might elucidate some mystery, to help us improve our ways of treating disease, or how we approach our aging process, and how we create new materials for use here on Earth too. So it's got some Earth benefits that we're already starting to receive. So it's a unique platform. You already know there's nothing like it anywhere else. All of our partners across the partnership, JAXA, ESA, CSA, Roscosmos, us, all participate in the research, so we share in that. We all have goals for human exploration, goals for Earth benefits. Right now, I think this orbital launch is going to enable the continuation and some new investigations of about a little over 250 science investigations over the next 6 months, and that's crazy. And it represents like almost 1,000 scientists from around the world. So the women and men that are up there now and who are going to be headed up there over the next 6 months will be busy doing all of your research in a way that's going to bring around the benefits that we all are looking to see. And so today, you're going to hear from some groundbreaking scientists who have never done anything what's about to be done on the space station before. And it's also going to pave the way for new capabilities. Particularly interesting are the new capabilities that are being added for molecular biology, and some studies of some of the changes that happen in physiological or living systems at a level you can't see all the time, but they're still always happening. So new capabilities for new scientists, and some technology development too, such as crystallizing different materials that could be used as radiation detection devices and such. So it's leveraging that microgravity environment, I think you all know, to be able to bring the benefits back home to us, and to allow us to explore further. And with that, I'll pass along to Mike Roberts.
Thanks, Tara. So Tara is here representing NASA, and NASA is obviously one of the primary real estate owners and operators of the International Space Station in partnership with the international partners. There is also on the International Space Station an orbiting national laboratory, the ISS National Lab. And the ISS National Laboratory is managed by a non-government organization, CASIS. That's who I'm here representing, the Center for the Advancement of Science and Space. Our mission is to work with NASA to offer opportunities for access to the International Space Station, to the space environment. So as Tara mentioned, the International Space Station is an orbiting laboratory. It's also an observatory. You've seen lots of pictures, I think, of Earth from the International Space Station. It operates in a unique environment that enables it to be utilized not only as a laboratory, because you have 24 hours, 7 days a week, 365 days a year free access to microgravity, which has very profound effects not only upon large organisms like humans, but also it affects even the smallest among us, the viruses, the bacteria, the archaea that live within and on us. And a lot of those molecular tools that Tara was highlighting upon are of interest to NASA. As we move farther away from low Earth orbit and go deeper into space, we need to take with us tools that we can monitor the health not only of the humans that are there, but also the health of the physical environment of the microbes that are associated with them. And you're going to hear a little bit about some experiments that are going to be conducted by students today who are utilizing cutting-edge molecular tools that will inform us about the environment's effect upon aging as we travel into space. In addition to being an observatory and a laboratory, the International Space Station National Laboratory is also a platform for innovation. So there are opportunities for STEM education. There are opportunities for students to not only participate in scientific experiments, but actually to propose experiments that they want to do in space. You'll hear more about one of those today. It's also a platform for innovation for companies, both large and small. So one of the main focus areas for the International Space Station National Laboratory is to enable access to space environment for commercial organizations who see in space a benefit to their product line or to areas of research and technology development they're currently engaged in. You'll hear a little bit about that today as well from companies that are interested in developing new scintillation crystals for radiation detection that can be used here on Earth or in space. You'll hear more about opportunities for small satellite launching opportunities through one of the implementation partners, NanoRacks. You'll also hear a little bit more about opportunities for materials testing in that environment. And you'll hear about some experiments that are focused on bringing those fundamental understandings of life and microgravity down to the physical level and the molecular level. And there are a lot of tools that are available to do that now that are being improved by actual utilization in the space environment. CASIS is not only focused, however, on the commercial side, we also work with other government agencies. Those are government agencies in addition to NASA, like the National Science Foundation, the National Institutes of Health, who are also seeking to exploit low Earth orbit for science investigations.
That's all great, Dr. Mike. Do you actually have a video for us, by chance?
I do. I have a short video we'd like to show you about the scintillation crystals experiment that's going on 087.
Why do humans care so much about science? Why are we so intrigued by research and learning? We're problem solvers. We want to dig into it and dissect it. We are just that kind of inquisitive people trying to answer the question of why and how and maybe when. The first 10 years of the station were about assembling it. We now have the opportunity to do research at a broader scale, a higher level. At any one time, there could be 200, 300 different experiments going on.
RMD has developed this new crystal, which is a scintillator. Scintillators are crystals which emit light when they are exposed to radiation. An experiment like ours, we can use universal hardware and platforms which are already on the space station. There's a huge, huge excitement factor. You feel like you live in a science fiction movie.
We're really working hard, both sides, NASA and National Lab and CASIS, to get new users to come in and do your world-class science on the station.
Excellent video. Speaking of how and why, do we have any questions from anyone in the room for Dr. Ruttley or Dr. Mike Roberts? Who's gonna be
Dr. Mike or
brave?
Dr. T?
Dr. How about
What training do student scientists need in order to make their way to your offices or maybe your projects?
So first of all, the orange fly suit did not throw me at all. It didn't even shock me, but it's so cool. So very cool. So students come from many different areas, and mostly most of the students for Space Station come through the National Lab effort. Dr. Mike will share that with you. But also, if you look up STEM on Station, there are lots of opportunities for students to participate in Space Station activities through there. But I'm going to let Mike share with you some of the specifics about student involvement.
Yeah, so I would say the one most important thing is imagination. It's about thinking of an idea, something that you think, how is this going to happen in the space environment, and bring that idea to it. So there are opportunities that can touch children at any age, from story time in space, we talked about briefly before. There are opportunities to simply enjoy an astronaut reading a story and understanding the way that life occurs in the space environment. I have two children, one who's 20, one who's 13. The younger one has never lived in an era where there were not humans in space, right? The 20-year-old, he's an old guy now. He grew up not knowing that humans were in space all the time doing cool stuff. There are opportunities through programs like challenge programs that offer opportunities for students to design payloads. There are opportunities for older students to actually begin designing small satellites where they not only can form a team that actually assembles the electronics and the actual part of the hardware, they can actually design experiments that go on inside them. So we're entering that realm now where space is accessible to everyone. It's not just a focus of the space agencies and the questions they have. It's really going to be at a point, not in the not too distant future, when you can probably go to some online ordering company and design your experiment and send it up for a reasonable amount of money. The way that we tend to operate in laboratories now, we send a lot of the analyses outside. And all we're going to do in the future is add more opportunities for space science to that.
Yeah, and those are really good points. And also there are opportunities through the Sally Ride EarthCam. If you look that up, it's managed by the U.S. Space and Rocket Center, and you can request imagery of certain areas from the space station. And then there's also the ISS ham radio opportunities too. So if you've got some ham radio enthusiasts, there are opportunities to get a group together and perhaps talk to the astronauts on the space station with the ham radio. And like Dr. Mike said, you know, I think if you're a student and you can think of any science experiments you've ever done, and you think of how it might behave if you take gravity away, I think you'll find that you might be coming up with some really new, creative, innovative ideas that Dr. Mike was referring about.
Great. So we do have 2 microphones in the room, so please do let us know who you are and where you're from as well.
My name's Debbie Reynolds. I'm from Pittsburgh, Pennsylvania. My question is about all the experiments that are going on up at the space station. So obviously all of the crew members that are there come from varied backgrounds. So what kind of training do they have to be able to run all those different experiments? Obviously they're not all biologists or physicists or things like that. So I'm curious about that, how they all get accomplished.
Right, so all of the astronauts who participate or fly up to the space station get trained in some aspect of the science. So usually payloads or the science experiments are assigned to crew members in advance, and they'll spend part of their 1.5-year training period. It'll be heavy on the science too. So they get trained specifically with the experiments that they're going to be working on, and that means they may get to know the principal investigator depending on how complex the experiment is. And all of our partners go through that. Once they're on orbit, they are proxy scientists, and so they actually work with our lead increment scientists on the ground here, but they also have an opportunity to call the principal investigators too from space and work through issues with them or maybe additional runs of an investigation with the PIs. So lots of opportunity to make sure that I'll tell you one thing, the astronauts absolutely own the science. They take full responsibility for it. That's what they care about. On orbit, that's their job. And so they're fully vested in the science.
I know we have other questions in the room. Do we have any questions online right now? Again, if you want to submit a question, please use the hashtag AskNASA.
Okay, so how do you ensure that the research, info, articles, data conducted on board the ISS are accessible to the public?
Okay, so I think both of us can address that, but if you go to nasa.gov/ISS-science, that's a repository of all the investigations that are performed on space station. We keep all content, and in that we also include a listing of the results, publications, scientific publications. But while that's our core, we also put out lots of communication products, such as web stories. You can follow us on Twitter at ISS_research. And so some of the fascinating results that come from space station science go out on social media. Also, they are posted on the ISS Facebook page. We do a lot of outreach. But really our focus is to make sure that the public knows as much as possible about the benefits that are coming back to you, and about benefits for exploration for space too. But we try publicly at the website, and then we take it from there by spinning off lots of different communication products.
Yeah, and there's information available on a couple of different websites for cases and ISS National Lab payloads. The most important one is to go to spacestationresearch.com. There's information on there that will provide you details about the capabilities that are there on station. It will have links to the publications that not only came from ISS National Lab, but from previous investigations that predate ISS National Lab. And there's a lot of opportunities just to ask questions. Part of CASIS's mission is taking the capabilities of research in space to a whole new audience. So we spend a lot of time at destination station events in partnership with NASA, speaking to communities about opportunities there. And we also have a very active STEM education program. So there's a lot of opportunities to learn about what's going on station. As a non-governmental organization, we also publish an annual report, which has lots of boring statistics and numbers in them. But there's information in there on all of the science and technology that's going up the station each year.
All great questions. I know there's many more in the room. However, we do have a number of other guests with us today. So if you don't mind, let's give a round of applause to Dr. T. For our next guest, we're going to hear from Dr. Howard Levine and Brian Onate to discuss the advanced plant habitat.
So I brought a visual aid. This is a plant called Arabidopsis, not your average plant. This is actually the most used plant for basic research on Earth and on the International Space Station. So the first science experiment that's flying on the advanced plant habitat will be using Arabidopsis. And if you have any further questions, I can elaborate later. I'm the project scientist for the advanced plant habitat, but why don't we go to the slides, if we could. This is Brian Onate, by the way. He's the project manager for the project, which has been 4 years in the making.
4 years in the making. So good afternoon, everyone. Project manager, what an exciting time to be actually flying this payload after working on it for many years. We had a white piece of paper when we started. They said, go build this, maximize the plant growth or the science area as much as possible, minimize the resources around it. That way we can grow plants from seed to seed and grow the largest plants we can on space station. So it's very exciting for us. If we go back to the slides real quick, what you saw in the picture there was our high fidelity prototype, and we call it the engineering development EDU. Everything's the alphabet soup that is out here. I'm just going to talk real quick about it, starting from the, I guess the left, working my way right. On the very left, there are 3 main components in there. I'm going to talk about 2 of them, and I'll talk about the last one at the very end. We have our power system in there. We have our water system for our plants. Moving our way towards the middle, you see that where the pink light is, that is actually the growth chamber. Again, it'll be the largest plant chamber, environmentally controlled chamber on the ISS, which is very, very exciting to have that capability up there. On each side of the chamber, you see these little modules on the side. That's actually our temperature and humidity control. And it actually allows us to control the temperature and humidity at various levels for the plants that they need. On the bottom corner, on the left, you see a drawer. That's part of the International Space Station that we got. And there we have our reservoir where we have our water. And we also have our CO2 tanks. And obviously, you see the pink lights. We also have a lighting system that goes up to about 1,000 micromoles, which is a scientific term that I will let Dr. Levine talk about. But it actually, we have the capability of producing about half the sunlight that you see. So if you were to go outside today, it's a pretty powerful light. And the mystery box. Well, in NASA, we have to give acronyms and everything and try to make it as cool as possible. We have a farmer. It's a PHARMER. It's the Plant Habitat, Avionics, Real-Time Management, and Express Rack. And there will be a quiz later. So we have a farmer. What does the farmer do? Well, the farmer is in charge of running the whole payload for us. We basically run about, I would say 90% of the payload from the ground. We need the crew members to put water in the system for us, do some maintenance activities for us to remove some filters. Basically, just make sure that the chamber or the payload is ready for all the plants. So it's an exciting time for us. I'm so glad that we're going to launch this very soon and get a lot of capabilities. And with that, Dr. Levine is going to talk to us about some of our first experiments we're going to do.
So if we could go back to the slides, please. So this is wheat grown within this EDU that Brian was talking about. So we're flying up the hardware on 2 rockets. We're flying it up on OA-7 and then SpaceX 11. So the hardware will get to station, it'll be put together, there'll be a checkout, and we're going to do a test germination of 2 species. One is wheat, and the other one is, what's this called? A Arabidopsis. So this is wheat. Let's go to the next slide. So this is a Arabidopsis. Again, it's a much smaller plant. We start off putting multiple seeds in each location to make sure that we have a good seed in growth and development. And you're going to see the next slide, we're going to be thinning these out. So now we're down to 1 vigorous seedling per location. Next slide, please. So here they are, they've grown a bit more. They're at what we call the rosette stage. Next slide. Here they are, it's just about week 4, and you're beginning to see the shoots. And we call it bolting. The shoots are sprouting forth upward, and you can even see the beginning of flower development at the top of the shoots. Next slide. So this is at about 4 to 5 weeks, so much more stem and flower development. Next slide. And then this is what it looks like after 6 weeks. So the great thing about Arabidopsis is it goes from seed to seed in 5 to 6 weeks. So it's a very short generation time. And it's also been completely sequenced for its DNA. So we know all of its genes. There's an incredible database in terms of when its genes do different things. There's hundreds, if not thousands, of strains of Arabidopsis, each one tailored for a specific purpose.
Great. With that, we'll open it up for questions. Right here.
I have a question. Hi, I'm Megan Charlotte from Indianapolis, Indiana, and I teach 5th and 6th grade science, and I wanted to ask you, you said you started with a blank sheet of paper, and now you have this very amazing piece of equipment. And to explain students the STEM and the engineering design process, can you kind of comment on some of the skills that your team has used? Was there a lot of teamwork, collaboration, communication, testing over and over? What are the skills that are needed to get from a blank piece of paper to something this impressive?
Absolutely, good question. Yes, very challenging. So NASA, we have a lot of engineering experts here. But first, we started with our scientists, right? When we went to our end, what I've come to find out is my customer. It's what I've learned through the process. He's my customer. I went to him, asked him, what do we need to develop? What do you need? He gave us a list of requirements. We also partnered with cases. So we went to our commercial partners and said, if we have this capability on ISS, what can we do? So we started with that. We used engineering, technicians, scientists. It wasn't just a NASA effort. We also worked with Orbital Technologies Corporation. They're a company out of Madison, Wisconsin. And again, they had engineering, technicians, scientists. So we partnered with all of them. And what is really cool, the picture you saw with the growth chamber, it's about the size of a mini fridge that you might have in your office. You know, that's as big as we can make it. Our local engineers actually fabricated that. They built the shell here locally. We machined it. So we, NASA, take a lot of pride because the science that's going in there was actually fabricated here by engineers at Kennedy Space Center. So very exciting. It takes a collaboration, skills all across the board to make this happen.
But the scientists are his customer.
The scientists are my customer.
Right here in the front row.
Claudia from Fort Lauderdale. I wanted to ask you, I mean, there are so many plants that you could choose from. How do you weed out which ones? How do you weed out which ones you want to use, which ones would work? That kind of thing.
So most of the science that flies on the International Space Station is what we call peer-reviewed science. So NASA puts out a solicitation saying, well, we're interested in this kind of research, and then scientists from all around the country submit proposals, and they submit proposals for particular species. So it happens that about 80% of the proposals are with a Arabidopsis. Yeah, a little bit better. However, as we get more and more into the exploration mode, we're beginning to shift into food-producing species, especially when we want to do what's referred to as bioregenerative life support systems, where we use plants for as food, but also to produce oxygen and scrub CO2 and purify water. So there's a lot of good things that plants do that complement humans. So there's a shift gradually towards that more applied aspect. So that's the wheat that you saw before kind of represents that category.
Quick check with our folks online. Do we have any questions from social media?
So we have a question from Jamers3294 on Twitter, and his question is very simply, so when will the astronauts get to eat a fresh salad?
They already have. Not from APH, the Advanced Plant Habitat, but from Veggie, which is up there currently. So that is our goal, and we continue to use the Veggie hardware that's up on station. And in fact, there's a second Veggie unit that is going up. I don't know if that was part of the briefing, but on this OA7 flight. So Veggie has about the same footprint for growing plants as the Advanced Plant Habitat, but it doesn't have the controlled environment that the Advanced Plant Habitat has. But that could be almost just as important, because as you scale up plant growth for food, you're not always going to have a very controlled environment, because it's very expensive and elaborate to create that controlled environment. So you may, in fact, have something like Veggie where you're just pulling in the air from the cabin environment and seeing how you can grow plants based on that limitation. And we've been successful in doing that, and we hope to expand on that.
And if I can add to that real quick, so Plant Habitat has 4 quadrants. So what we could do in the future is we could plant 4 different, for instance, make a salad, lettuce, tomatoes, onions, peppers, and they all have different growth cycles. So what we could do is actually start them individually, so that way they can harvest all at the same time, and they can have a salad straight across the board as if they went to the local grocery store. So it's just an option. I'm just throwing it out there to my customers. So.
To my customer.
Sounds delicious. We have time for one more question in the room here in the back in the green, please.
So are you considered the Mark Watney of NASA, and are you planning on growing potatoes?
We're not currently planning on growing potatoes in Advanced Plant Habitat. It's possible. However, members of our team here at Kennedy Space Center are growing potatoes in simulants regolith, as you would find on Mars. So that work has started. In fact, it started a number of years ago. It's not that we just started it, but that's an ongoing effort. I can't claim to be Mark Watney.
I don't think anybody can. All right, thank you both. Appreciate it. Thank you for the show and tell. You brought what, guys?
A plant.
So much better. But thank you again. And our next guest is Saurabh Sinha, and he's going to talk to us about ADCs and microgravity, and starting with what that means exactly.
Okay. Well, thanks for having me here. It's really great to be here. I've been working on this project for about 2 years now, so finally seeing it come to fruition and getting ready for takeoff here. So what we do, Saurabh Sinha, Chief Executive Officer of Oncolinks Pharmaceuticals, what we do is we develop targeted cancer drugs that don't have any nasty side effects of chemotherapy. So what that means is we take supercharged chemotherapy, we link it to a carrier molecule, gets carried directly to the cancer cell, and then it binds onto that cancer cell, releasing the drug just for the cancer cells and not the healthy cells. So that's really a way to avoid all those side effects like nausea, hair loss, the anemia, all those other nasty side effects that are commonly associated with chemotherapy today. Now, what we really hope to do on the International Space Station is bring some of that microgravity environment and the unique microenvironment of the tumors in microgravity back here on Earth. So basically when we do research on Earth, we have those cancer cells laying flat in a petri dish. But that's not really how tumors evolve or grow in your body. So solid tumors actually form these spheroids. So in microgravity or no gravity, these cells will float around and they'll bind onto each other and they'll actually form these spheroid tumor models. Basically, the microenvironment of those spheroids are very, very different than what you would find in a petri dish where the cells are just laying flat. The inside of those balls are very, very hypoxic. There's no oxygen that gets into the middle of those spheroids, and actually the tumor cells are actually dead, so it's only the outside of the spheroid and the solid tumor that's actually growing. So what we really hope to do is study that microenvironment, figure out exactly how our drugs are metabolized in those solid tumors, so that way when we move into clinical trials, hopefully in the next couple of years, we'll have a better understanding of which drugs work the best for which tumors, and how we can really optimize these drugs to treat as many patients as possible. So with that, I'd like to thank NASA, I'd like to thank CASIS, I'd like to thank the University of Buffalo, BioServe, all our partners, and the University of Houston who partnered with us on this, and I'll open it up for questions from there.
Great, we'll start with questions from the room. Right here in the second row, please.
On Earth with the 2D Petri dish apparatus, we know you got put the film, you look at it with your microscope. So how does that apparatus change, or how does it look differently in capturing that in 3D in space?
Great, so maybe this would be a good time to bring up the slides and I can answer that exact question. We'll go to the first picture. So basically we have these biocells, and that's exactly what I'm filling there with Luis Zia, who's a really great engineer from BioServe. He did a lot of great work for us. And in these, what's called biocells, the cells will be deposited there. They'll float around. We actually put in magnetized molecules that help the spheroids form much quicker, so then we can get to testing them much quicker. And basically, we'll use microscopy and fluorescent microscopy to really image the cells. And we can actually see these spheroids forming over the course of days. They'll start to form very small, and then once they sort of latch onto each other and form these initial balls, and they grow very rapidly from there. Then we can go to the next slide. The next picture there, that's Luis Zia, myself, and Matt Malone, another BioServe engineer. That's the PHABs, the biocells, and our syringes with all the drugs and cells loaded into them. So those are the last human hands that will touch them here on Earth until they're opened up on the International Space Station. So any other questions?
Question right here in the front row, please. Just wait for the microphone.
Do you have any particular type of cancer that you're targeting right now, or are you just doing generally all different types of tumor cells?
Great. So great question. So the cells that are going up on the International Space Station are lung cancer cells. But what's most unique about antibody-drug conjugates is that we have that targeting molecule that will carry that supercharged payload right to the cancer cell. So if you swap out that targeting molecule, you can actually carry it to lung cancer, or breast cancer, or colon cancer, kidney cancer, and so on. So you can actually target many, many different cancers using just one target molecule.
Great question. As a reminder, if you're watching online, please use the hashtag NASA to submit a question. Sarah, any questions? Anyone else in the room? Anything else to add, Sarah?
No, just looking forward to launch tomorrow.
Sounds good. Thank you very much for being here today. And our next guest, we're going to hear about Genes in Space, a student experiment. This is Julian Rubenstein, and we have Dr. Sebastian Craves from Genes in Space.
Thanks very much. Genes in Space is a national science competition inviting students in middle school and high school to design a DNA analysis experiment that can help us tackle a question posed by space travel, an opportunity or a challenge of space travel. And every year we invite kids in grades 7 through 12 to respond to this challenge by designing an experiment that utilizes the unique capabilities and microgravity environment of the ISS. Last year, 2016, we received over 380 proposals representing around 1,000 participants from across the country. And the top 5 were invited to receive mentoring from scientists at MIT and Harvard, and they came to present their projects at the International Space Station R&D conference in San Diego, where Julian Rubenstein emerged as the winner. Today we will hear directly from Julian about his experiment to not only answer a fascinating and relevant question about space travel, which is what happens to the end caps of our chromosomes as we travel through space, but Julian's experiment is also helping us build further capabilities for molecular analysis aboard the ISS. And it's been a really fascinating year, 2016, for molecular biology in space. I'm a molecular biologist, so I get very excited about this. We had the first DNA amplification experiment successfully carried out. This was also designed by a high school student, the winner of the first Genes in Space competition, Anna Sofia Bogorayev. And we also had another major milestone, which was the biomolecule sequencer payload, carrying out the first DNA sequencing experiment. And these two techniques are really significantly enhancing capabilities for DNA analysis in space. And together, they're game-changing for space exploration. So in this payload, we're having the luxury of not only flying Julian's winning experiment, but also combining the mini PCR and the MinION sequencer together. The biomolecule analyzer project was carried out independently of us by a group at NASA's Johnson Space Center that we've since started collaborating with to enable the complete workflow to allow us to take a sample on the ISS, amplify DNA, sequence that DNA, and answer what microbes are coexisting with astronauts on the ISS. So Genes in Space, for context, is a collaboration, a partnership between several companies. Mini-PCR, we're the makers of the DNA amplification technology that serves as the basis for the competition. Boeing, Cases, New England Biolabs, and MFA. And it's extremely exciting that a partnership between private sector, biotech, aerospace, space agencies, and the public is helping push forward the space research agenda. And we're extremely proud to introduce Julian Rubenfein, winner of the 2016 competition.
Hi everyone. Super excited to be here. This is pretty cool. Love the flight suit. That's amazing. And it's great audience, teachers and everything. Really pumped for the launch tomorrow, or April 18th. Fingers crossed. Love all of the science, Arabidopsis, huge fan. ADCs, I love, immuno-oncology, all of that. So I'll talk a little bit about the science that we're going to be setting up tomorrow, April 18th, fingers crossed. Right here, I have a little nifty machine. It's called a mini PCR machine. And I'll go into all the details and everything, but sitting on this spacecraft right now, on the ground is one of these, and there's some tubes alongside it that are really similar to these, and I'll tell you all about those. But when our astronauts on the space station receive these things a few days from now, they'll be able to run a preliminary test of an assay that scientists will be able to use in the future to investigate telomere dynamics aboard the space station. So I'll explain all of that. I'll get into the weeds. You can tell me if I'm getting too technical. Huge nerd. I love all of this. But I'll just contextualize it first a little bit. So, the next sort of great journey for mankind in terms of manned space exploration is, of course, the manned mission to Mars. That's what everyone's pumped about. That's what everyone's excited about. Everyone's working on that. But day by day, it's becoming more and more clear that humans aren't, you and me, we're not biologically primed for that kind of long duration mission. So if we send astronauts up to the space station for a short mission, 6 months or something like that, they go up there and they encounter really numerous significant health problems. So we're talking about things like increased risk for cardiovascular diseases or atherosclerosis. I mean, everyone knows about like the loss of bone density and all of these types of things. They're really serious. So, and everyone also knows that if you increase the mission duration to something like 9 months to go to Mars or something like that, and you're going into deep space with more cosmic radiation, all of that, the symptoms get worse and worse. So it's important that we understand astronaut health before we attempt something really ambitious like that. So the current platform for doing that kind of research is the ISS, of course. Super cool. Over the last few years, the volume of molecular biology research, specifically on the ISS, has increased exponentially. And likewise, the data that's come down about physiological, genetic, epigenetic, transcriptomic, metabolomic changes in astronauts, everything from the microscopic level to the macroscopic level, that's increased exponentially as well. So we're learning a lot. And what I've been focused on, for the past year or so with all of the people who've been assisting me is really a very specific genetic change that can occur in astronauts when they go to space. And that's a change in the regulation of their telomeres. So I have a little visual here. This is just one of my shoelaces. So if you try to think, it's fine. If you try to think of a telomere, a good way to think of a shoelace, it's sort of a protective cap made out of DNA and protein. We would say a nucleoprotein cap. It's repetitive on the tips of all of our chromosomes. So all of our cells, they have chromosomes, 46 of them, and on the tip of each of one, there's a little telomere. So if you think of the shoestring like a chromosome, then the little plastic tip, the aglet, I think is the term, is like the telomere. So it protects the shoelace from fraying. Telomeres protect chromosomes from all kinds of damage that can be incurred in a cell, all types of things all the time. So they're obviously really crucial. And likewise, you can assume from that the regulation of telomeres, especially telomere length, so whether they're too long or too short, that's something that's really closely controlled in a cell. That's really important. So there's been a lot of research on Earth into what happens when the length of a telomere, especially, gets out of whack. So aberrant regulation of telomere length, that's a big thing. And there have been a lot of sort of connections to a lot of diseases that humans experience on Earth, especially in the elderly population. That's because our telomeres get shorter naturally as we age, depending on the cell type. So we're talking about things like cardiovascular disease, again, different cancers, insulin resistance or poor immune function, all of these types of things. So NASA is really interested in this. And that is primarily because when astronauts go to space, all of the stresses that they go through, microgravity, cosmic radiation are the big ones, but poor quality of sleep, it's really hard to sleep in microgravity apparently, poor nutrition, all of these things lead us to believe that the regulation of their telomere lengths in different cell types within their bodies, that is sort of weird, sort of wonky. That gets, sort of out of whack, like I said, when they go to space. So it's something NASA's interested in, and we know that's true. The telomere regulation in space is abnormal in some people, because when Scott Kelly came down from his almost year in space a few months ago, in some of his blood cells, preliminary data shows some of his telomeres got significantly longer, which is kind of a weird result that's kind of difficult to explain right now, but it's really interesting and meaningful for future spaceflight. So that's why it's important to study telomeres. When I was thinking about this last year, the next question was really, what's the best way to go about looking at something like this? If you're a team of scientists and you're interested in telomeres, how do you do that? Well, if you're like the scientists who looked at Scott Kelly's telomeres, you prepare materials on Earth, you ship them here to KSC, you put them on the rocket, lift off, you collect samples in space, you have to prepare those, you send that, you ship it back to the lab, all of that, and that's worked fine and it's been great, but you can imagine how when you scale something like that up to a longer duration mission, it quickly becomes inefficient. So there's a bit of a bottleneck there for this kind of molecular biology research. So the holy grail, so to speak, for this kind of thing is a platform where we can do these kinds of investigations on the space station in real time on orbit without having to send stuff back and forth, giving astronauts full autonomy. So I'll just talk super quick about this. Sorry. So this is the mini PCR machine, polymerase chain reaction machine. Basically what we do is we get these little tubes like this. We add water, we add DNA, we add enzymes, and we put them in here, turn the machine on a few hours, and the machine will actually copy the DNA billions and billions of times. So we can do this with telomeres because telomeres are mostly DNA, and we get tons and tons of telomeres that we can then analyze, so that's important. And this is actually small enough, along with this, that we can use it on the space station. So we send these up, and eventually astronauts will be able to isolate DNA on the space station and perform this kind of assay, gather all kinds of data. You can think of you know, setting up model organisms like Arabidopsis, or we also have mice up there, yeah. Little rodent astronauts, all types of things, periodically keep them there for generations. You could do this with astronauts too. Collect their DNA over time, have them perform the assay on themselves, gather all kinds of data that we've never had before. So really
Thank you,
exciting.
Julian.
Yeah.
I don't want to cut off somebody so much smarter. Oh my God, you guys know that he's 17? 17? We have time for just one or two questions if we have any in the room, please. We'll start right here in the front row.
Okay, so I said, by the way, congratulations. That was very impressive.
That made sense.
Yeah, sort of. So, like I said, I teach 5th and 6th grade at Little St. Barnabas, Indianapolis, and then I'm also part of this program called the Trustees and Teaching Fellows at the University of Notre Dame. So I have students in middle school all across the country are watching this right now. What would you say to them to get them to sort of, as an inspiration that you are? What's your message?
Okay, I mean, to do this type of work, it's actually a totally unique opportunity. I can say kind of easily that the field of space science and space biology is so nascent that it's actually possible for me as a high school student to make a significant scientific contribution to really advance human knowledge, in a small way, but that's more than enough. I mean, you don't have to be a professor or a career government scientist or something. There's so much that needs to be done before we can do a Mars mission that it's like all hands on deck, So if you come up with something creative or something that, nobody's even been able to do yet, there's all sorts of opportunities.
Great. Any more questions in the room? Question from online?
Okay, so I have a question from Twitter from Lauren Loise. And her question is, what does amplification of DNA mean, and how is this done? Can you look at telomeres and their action?
Thanks. I had to rush through that part. I'm sorry, but amplification is like what I said. You throw the telomeres into this machine here, you turn it on, and amplification is when you make billions and billions and billions of copies of that DNA. And DNA is such a small molecule that to do any kind of real analysis with it, you have to have a lot of it. So it's an essential precursor to any kind of analysis technique that we need. So the reason that this is what we're doing in the mission tomorrow before we can do the full assay is that, as any molecular biologist will know, not all PCR target sequences are created equal. So a really repetitive region like a telomere is going to be tricky to amplify on Earth to make a bunch of copies of, not to mention microgravity. So we're just testing this out. Did that answer the question? Okay.
Any more questions in the room? One more time. Up front here.
I just want to know where you go to school and what kind of school and how did you...
I have to balance this. I have a few tests when I get back. No, actually, I haven't started studying. I go to Stuyvesant High School in New York. It's a math and science school, but I also love reading and writing in Lower Manhattan. This was mostly done outside of school. This was something I initiated myself after talking with my teacher about it a lot. And then it's been, working in labs all over the East Coast, since then, at NYU, at New England Biolabs, our partner.
And I'll just add, this is an annual competition that we run every year, and it's currently open for its 3rd year of submission. So students across the country in grades 7 through 12 have until April 25th to come up with a killer idea. They can be standing
Hop
right
on
there
it.
next year.
Great. Well, thank you so much, and congratulations again, Julian. And now we have Henry Martin and Davide Masudi to talk to us about some of the CubeSats that we're sending to the station.
Yes, good afternoon, everybody. My name is Henry Martin from Nanoracks, and today I'm going to talk mostly about the satellites which we are launching up to the ISS on April 18th. So I have some slides. Could you throw them up there? Anyway, so NanoRacks, we don't only launch small satellites. We do a lot of stuff on the ISS. By the April 18th launch, OA7, we will have sent up over 550 science experiments to the ISS. They'll range from internal research, so plants, DNA, all sorts of different things, to also satellites, things on the outside of the station, etc. Tomorrow we'll be debuting mostly the top two, so the CubeSat deployer, which goes out of the Kibo airlock, which is run by the Japanese component of the ISS, and then we'll also be using the outside of the Orbital ATK CRS vehicle to launch at a higher altitude. Next slide. Cool. So we're launching 38 satellites total, and 34 of them are going to be through the inside. So this is a shot, just an example of, we shoot out anywhere from like 1 to 3 at a time, and then they go off into space and do whatever they were meant to do. There's a broad range of things satellites can do, really anything, and right now they're getting a lot smaller. These are 3 CubeSats here. Next slide. Here is a snapshot, cool picture of the external CubeSat deployer that we have. So there's a white box kind of on the left, bottom left. We actually mount that on the outside, so it never goes inside. Crew never has to touch it. Once the Cygnus leaves, it will, pending all nominal operations, go to a higher altitude and shoot them out, giving the CubeSat customers more lifetime. These CubeSats here are going to do commercial weather, so they'll take the data and they'll sell it to people who ever need to track ships, and they also track ships themselves. So like AIS receivers, most of them are ground-based. Once it goes about 6 miles offshore, you can't really track the ship. If you put it on a satellite, you can track it wherever it goes. So next slide is really here my colleague and partner Davide Masuti. 28 of the satellites we're launching internally are part of this QB50 mission. And QB50 is a very cool mission, which you will hear about from him. But what's cool about this slide is it is a huge collaboration effort among engineers, scientists, all sorts of people who made this happen. They've been working on it a very long time. I personally, with another colleague, have been going at it for about 2 years now, and we are very excited to get it up. So with that, Davide.
Thank you, Henry. So, good afternoon to everybody. We are very actually excited to be here. We're coming from Europe to present you this project. So, can you put the slide, please? So QB50, it's a real international project. We are going to launch a constellation of CubeSats, 28 for the precision, to investigate the mid-lower thermosphere. Next slide. So the 28 CubeSats, in fact, are manufactured and designed by students, universities, coming from all over the world, literally, all 5 continents. There are more than 15 countries involved in this project. So in fact, it's truly international collaboration. So the project is coordinated by a consortium led by the Concamerone Institute for Fluid Dynamics and received funding from the European Union. And we have 15 partners taking part of the consortium, 15 professionals. So when the project was conceived, we conceived the project with 4 objectives in mind. The first is facilitating access to space. So we're providing students and universities easy access to space. So what we do basically is we're following them, we are supporting them from design to manufacturing to integration and launch. So we're providing them support, technological support for designing their CubeSats. That we do, in fact, we do also orbital, so in-orbit demonstration. So we have, of course, students design their own CubeSat, testing their own technology, so we're providing a platform for in-orbit demonstration. We're also doing education. In fact, what we do is we are trying to educate future research and space engineers. So we are also fostering international collaboration, which is the most important part in QB50. And lately, last, in fact, we do also science. That's why we're here. So what we do is we're trying to launch a constellation of CubeSat to investigate the lower thermosphere. Now, why we're doing that? So the lower thermosphere, in fact, is the mostly unexplored region of the atmosphere. It runs between 200 and 400 kilometers altitude. In fact, the lower thermosphere is too low for these satellites. In fact, it's lower than the International Space Station, but it's also too high to be reached by rockets, small rockets, in fact. So CubeSats provides the perfect means, the perfect way, the perfect tool to explore, to do in situ measurements of the thermosphere, so provides the tool, in fact, to do these measurements. So what we do, in fact, we have the CubeSats, which are built by the universities and students, and then as we, as a consortium, we provide them an instrument. So all these satellites, in fact, has one instrument provided by the consortium to measure the chemical composition of the thermosphere. So now, why it's so important to analyze the thermosphere, the mid-lower thermosphere? In fact, the mid-lower thermosphere is the area in the atmosphere where the space shuttle flies, for example. Of course, you have a lot of space debris, and you have a lot of satellites there. So, thanks for the slide. So, in fact, knowing the density, in fact, will provide us a better knowledge of the thermosphere, will provide a better tool to predict, for example, assess the trajectory of space debris re-entering the atmosphere, for example. And we also provide better tool for predicting, for example, station-keeping maneuvers or collision avoidance maneuvers for the space station, for example, or other satellites. And the late also, of course, all these results that coming from the constellation of sensors will also provide a database that will be used by scientists for many years, will be used for enhancing modeling, forecasting modeling of the thermosphere. In fact, most of the, the models are physical models, and in fact, the knowledge of the physical, so the chemical composition, also the electrical phenomena in the thermosphere will, in fact, help scientists to do better modeling of the thermosphere. Now, if you go to the next slide, please. Right, here we have a lot of the CubeSats. We have 28, in fact. All of them are different from each other. So in fact, during QB50, we tremendously learned that the same objective can be, or the same objective, in fact, can be reached by 28 different ways. So we have 28 CubeSats. Each of them, as I said, has a single science payload or an instrument provided by us, and all of them will contribute to create this database. So in fact, what we're going to have is the first coordinated in situ measurement of the thermosphere. Okay, and this is also the first international collaboration where we are coordinating basically CubeSats from all over the world. So just to conclude for the next slide, please. So QB50 has a number of firsts. We have 28 CubeSats in an international collaboration. So actually, it's a constellation that will provide us with multi-point measurement of the thermosphere, of the lower thermosphere. And there are 3 sensors, as I said. There is a ion neutral mass spectrometer, a flux probe, and a linear probe to measure different chemical components of the thermosphere, also the electrical content of the thermosphere. We receive fundings for 9 million from the European Union, but in fact, this covers only the launch and the support. But you have to consider that all the rest, so the bus, the CubeSat, have been manufactured by universities. So in fact, if we think about how many universities, how many people we involved in the project, we can think about having involved at least more than 50 professors. I suppose this is really the lower boundary of my estimation, and more than 300 students that were involved in this international collaboration. And we also produced an average of 10,000 pages of documentation, where in fact we had to review. So we are very proud of this mission, of course. We tremendously learned, and we're extremely excited to be here today. Thanks a lot.
Great, thank you both. Unfortunately, we're right at the top of the hour, so we can sneak in one quick question if there is a question from the audience right now. Right here.
Hey, I'm Doss with the Kerbal Space Academy. We've been talking about CubeSats and the size of CubeSats and stuff, but a lot of people don't really have an indication of how big a CubeSat is. My question is about how big are these CubeSats you're talking about, and would my little guy here fit?
Sure. Well, the CubeSat we're talking about can be modular, but the CubeSat we're talking about is a shoebox size.
Shoebox size. So he would kind of fit inside of one. A lot smaller than a normal satellite.
Yeah, he could go.
Gotcha. He could go. Thank you.
All right, thank you, Henry. Thank you, Davide. I believe you'll be around later for additional questions. That is going to wrap up our What's on Board briefing part 1, talking about the science that we are sending to the International Space Station aboard a Cygnus spacecraft. Again, our launch is targeted for April 18th at 11:11 a.m. when a 30-minute launch window will open. If you're watching live, please stay tuned. In another moment, we'll come back and we'll discuss the Atlas V rocket and the Cygnus spacecraft with mission experts. Thanks and have a great day.
I had to ask the question. I mean, give people a sense of scale of how small the CubeSats are. They're like, CubeSat, CubeSat, CubeSat. How big's a CubeSat? Well, Jeb will fit in a CubeSat. Yeah, it's a standard size. Yeah, it's like a standard size, the 1U, 2U, 3U, yeah. Just the whole, the launcher thing. It's like a standard size. You put your package inside of that. It goes into the little deployer. It goes up on the ISS. Some of the upper stages carry them. That's why I want to ask the question, because it's like, they're talking about, they're smaller satellites, they're cheaper to launch, and it's like, well, how big are they? Well, they're really small, actually. Hello. Hi.
Hi, I'm also from the QB50 project.
Oh, thank you.
I was wondering if your little guy would like to have the mission site.
That would be fantastic. Thank you very much. I appreciate it.
Where are you from? Where are you posting?
So I am streaming on Twitch right now, and we do like a Space Academy sort of thing where we use video games to help people understand space and science.
That's really cool.
Yeah.
I should have your Twitter account right now.
That would be fantastic. Just a second, chat. I'm busy. We're live right now, by the way, so they can see you. Which is okay. Thank you very much for the wait, chat. Look, you got a patch. How cool is that? I'm K Space Academy. Like the letter K Space Academy on Twitter. Yeah, thank you very much. We'd love to have somebody come on the show and talk with us. If you have a scientist or something that wants to talk about what y'all do, that's something that we do. Go back live. Everyone behave.
Yep, I got you. All right. There we go. Yep. All right, we're gonna do one of those rousing applauses and hooting and hollering. Right? Yeah. You guys ready? Okay.
Stand up and do some jumping jacks.
We're gonna go live.
Gives it like a 10, 9, 8.
Indeed. Oh yeah, we'll give you a countdown. Don't worry. NASA knows how to do countdowns.
Oh man.
You're so good with your food.
Someone better be tweeting all these.
Oh, I've tweeted a couple so far.
On it.
We are 30 seconds out. Hi everybody, and welcome back here today to NASA's Kennedy Space Center, where on April the 18th at 11:11 a.m. we're going to be launching the Orbital ATK Cygnus spacecraft carrying cargo and supplies to the International Space Station. For those of you who are just joining us, we are here live and going to talk a little bit about the spacecraft and the rocket that it's going up on, which is a United Launch Alliance Atlas V rocket. And so joining us to talk about some of this, though, jumping straight into it here from the United Launch Alliance, is Joe Foose. If you want to follow them on social media, you can follow them at ULA Launch. And so without further ado, let's talk about the rocket.
All right, so I have some slides to pitch. So if you can bring up the first slide, as I thought. My name is Joe, and I'm with United Launch Alliance, and I'm representing launch operations of many different systems on the rocket, up into my current position as spacecraft integration. And so we have a picture of our rocket here in separated sections, and this rocket will provide the high-tech muscle for tomorrow's launch. And you can see the first section is a brown section, like a tan color, and that's the Atlas booster with the RD-180 engines attached to the bottom with the engine thrust section at the bottom. The interstage adapter, and then the second stage center. Well, let me stop right there. The booster and the center are made at Decatur, Alabama, and shipped down, and then dropped off at the port and delivered to us for processing. The interstage adapters and the payload frames are made in Arlington, Texas, and shipped over to us. We process all of these in a combination of 4 or 5 different buildings. Get it all ready. We erect the Atlas booster first in the VIF, the vehicle integration facility. The interstage adapters. The second stage comes over. We put that up on top and get ready for the spacecraft, which is being processed in its own facility. Get ready to go. It is encapsulated, and the encapsulated assembly, we call it, the payload and the fairing, come out together and get set on top of the rocket about 2 weeks before we launch. The whole launch time is about from launch from 11:11 to about 4 minutes in, 4.5 minutes in. The whole booster is done and it separates. We're left with the Centaur, the second stage, which burns for the rest of the time until separation. Typically 30 to 45 minutes from T0 from launch time, and we're separated. And our muscle part is done, so we're done in less than an hour, easy. And we put you in orbit, and the spacecraft finds its way home, whether that, in this case, off to the space station to make it to the space station. Second slide. So this is the launch complex. Right now, it's a perfect representation of what's there right now that was rolled out this morning. Started at 8 o'clock. The vertical integration facility is the building that's off to the left-hand side of the picture. It's about a quarter mile away from the center of the launch pad. The whole trip took less than an hour to roll out. It's walking speed that it rolls out at. It sits right in between these 4 lightning tower masts that protect us from any lightning for the night's stay out there. We roll out typically the day before we launch. And then in the afternoon today, matter of fact, we filled the booster tank with RP1, that's highly refined kerosene. Tomorrow we'll do cryogenic booster with oxygen, liquid hydrogen in the rest of the first and the second stage. And then and we start that about 2 hours before we actually launch. So there's lots of preparations to be done. The guys come in, the whole crew will come in probably early in the morning, like 2 o'clock and 3 o'clock in the morning, get ready for that last 2-hour cryogenic load and launch. I believe we have a video. We can play that now.
The following profile details the important events of this mission using approximate time.
5, 4, 3. We have Atlas ignition. 2, 1, 0, and liftoff. We have liftoff of the Atlas V rocket.
The Atlas RD-180 main engine ignites to lift the vehicle away from the pad. Shortly after liftoff, Atlas begins its initial pitch, yaw, and roll maneuvers to attain the proper ascent profile and minimize aerodynamic loads. The Atlas V reaches Mach 1, a speed of sound at 83 seconds. At 94 seconds, the vehicle experiences maximum dynamic pressure. Approaching booster engine cutoff, the Atlas V is running propellant at the rate of 1,350 pounds per second, traveling at approximately 10,000 miles per hour, and located 79 miles in altitude and 172 miles downrange. Booster engine cutoff occurs 4 minutes and 15 seconds after liftoff. 6 seconds after booster engine cutoff, the booster stage is jettisoned. The first Centaur main engine start takes place 10 seconds after booster separation. The payload fairing is jettisoned approximately 4 minutes and 40 seconds into the flight. Cutoff of the Centaur main engine follows a nearly 14-minute burn. The mission now enters a short coast in preparation for spacecraft separation. At 21 minutes, Centaur releases the Cygnus spacecraft for Orbital ATK and NASA.
And that's the mission profile.
Thank you very much.
All right, wonderful. So we are going to now talk about that particular spacecraft that was there at the end of the video. And that comes from Orbital ATK. If you want to follow them on social media, you can find them at Orbital ATK. And without further ado, here's Paul Escalera to talk all about the spacecraft. Paul?
Everybody here? So I work at Dulles, Virginia, which is where we manufacture the Cygnus spacecraft. And so I supposedly know everything you guys want to know, but we'll see. And let me point out, as all of you are, we're very excited to be here, especially on the eve of the launch. This was kind of been a long time coming, so we're very excited, to get this off the ground tomorrow. So I do have a video that I'll speak to, so why don't we go ahead and cue that. And this video will tell us a little about Cygnus, its cargo, and its mission. So it'll first start with a view of Cygnus itself and our OA7. So, as you know, we'll be launching Cygnus for the 3rd time on an Atlas V launch vehicle. And here's some video from one of the last times we launched Cygnus on an Atlas. And Cygnus is loaded with about 7,600 pounds of cargo, which is a lot. And we expect to be at station for about 90 days. So we'll get to that later. So Cygnus is comprised of 2 modules. First shown here is our service module, which is manufactured at our Dulles facility. It has all the brains, the propulsion, the guidance and navigation, and comm system necessary to do the mission. So you see here, it's a pretty complex looking spacecraft, but it gets the job done. Our other module or piece of Cygnus is our pressurized cargo module, and that's manufactured by Thales Alenia Space in Italy. And shown here, it's arriving at the launch site, and this is where we put all the cargo, at least the pressurized cargo. So upon arrival at the launch site, we load some cargo in, and we prepare it for mating with the service module. So the service module will arrive at the launch site about a month later, and as you see here, we're mating the 2 pieces together. So this will make the whole Cygnus spacecraft. After mating, we load it up with fuel, and we do another final cargo load into the spacecraft and prepare it for launch. You'll notice our PCM is very large. This is our enhanced PCM. It's what we've been flying since 08-4, so it carries a lot more cargo than some of our earlier missions. The service module itself is also optimized for this mission, and it features our innovative ultraflex solar arrays, which are shown here in deployment, and these are manufactured at our Goleta plant in California. So once we arrive at station, the crew opens us up and starts unloading all the valuable signs and cargo, fresh food and things of that nature, and then they fill us up with trash. Once that's done, they send us on our way. However, our mission is not complete. We still have some secondary objectives, and we have some secondary payloads on Cygnus, which include the Sapphire 3 fire experiment, which studies fire propagation in zero-G, and here's some video from one of the last times we flew Sapphire. Very successful mission. As you heard earlier, we'll also deploy some CubeSats out of the externally mounted NanoRacks deployer. And then finally, we'll also have the Red Data 2 flight recorders. And these flight recorders will record the environments
while we're re-entering into the atmosphere. So pressures and temperatures and things of that nature. However, in order to execute this part of the mission, we've got to deorbit Cygnus. So we'll do that, and we'll safely dispose of Cygnus over the ocean so nobody gets hit by anything. So finally, we're very excited to support the ISS and its crew by delivering cargo, science experiments, and also doing these secondary missions like Sapphire and these CubeSat deployments. And we do look forward to missions beyond this one, as we have many more lined up and ready to go. And we look forward to supporting ISS and NASA. So, go Cygnus. Thank you.
All right, everybody. For those of you who are following along online, we're getting ready to enter into some question and answer here. You're welcome to ask questions using the hashtag AskNASA. And we'll also take some questions from here in the room. Questions all about the rocket and the spacecraft. So who's got the first question teed up? Who's ready? All right, we're going to start down front here in the orange, and then we'll work our way back around.
Hi, Valeria Rodriguez from Miami School Gulliver. And I wanted to know, when the video was showing that all the different pieces were coming apart, do those get collected and reused, or where exactly do those pieces go?
So every part on the Atlas V is expendable. Right? Truth drops off into the ocean. Centaur will eventually deorbit and drop off into the ocean, just like the spent cargo module. And the fairings, when they separate, they fall off, and they fall off into the ocean. They come off pretty soon, so they all fall into the Atlantic. So it's an evolved expendable launch vehicle. That's the expendable part.
All right, next question will be in the second row here in the black shirt.
Hey, Lincoln Neely from Dallas. And I was wondering which part for both of y'all is the most sensitive part of the process, prone to error, and have y'all ever experienced any critical alarms or very serious possibilities of failure and had to do some real-time problem solving in the launch or the space vehicle?
I don't know about Joe, but we never had problems. Throughout the build of these spacecraft, we have to understand that they're very complex. And oftentimes, you do a test that you've done 50,000 times before, and something doesn't go quite right. And we have processes in place, to investigate what the problem is and why it occurred. And the team is very skilled in executing those processes. Not because we have lots of problems, but because that's how we do our business. And, so we roll with the punches. We always want to meet our launch schedule. These guys are ready and waiting for us, so we have to get through these failures as they come. So, it's always something going wrong, but we have a very skilled team that can overcome those problems.
And the launch system can consider that. We have a very experienced launch team, and anything that comes up, we can solve. And the part that really gets tense for us is when we integrate operations. When you're done with your processing your spacecraft and your fuel, and you hand it to us to encapsulate. And that's your baby, and you don't want us to break it, and we will not. And we work together. It's integrated operations. We work together to encapsulate and transport out and carefully pick it up and set it on top of the launch vehicle. Very critical day. It's a 24-hour day plus day that we do that. And then once that's on there, we do a couple of integrated tests, make sure everything's all connected right. And the last day, the launch day, is almost the easiest day. We're back to where everything is ready, the trigger is set, we just sit back and load it with fuel and launch. It's the easiest day.
All right, next question's in the back here.
Hi, Amy Stilling, producer of Nature Film. I have a question about the Sapphire project. What questions are you hoping to investigate and get answers to with Sapphire?
Great question. Well, let me start off by saying the Sapphire experiment is from NASA Glenn Research Center. So we integrate that experiment into the pressurized cargo module, and then we work with them post-departure to execute that experiment. I'm not going to necessarily speak for them. However, I will say that they're trying to understand how fire moves and propagates in 0G for different materials and different accelerants. So these samples that they have, in some cases they have more than one sample that they set on fire. They're just trying to understand how these things burn, how much smoke they get, and things of that nature. And for us, it's also a good chance for us to test our smoke detector on Cygnus. So,
All All right, wonderful. There were questions over here. We'll start here in the blue.
Hi, my name is Brian Lauer. I'm from Boston, Massachusetts, here with History Review VR. We were wondering, based on the history of rockets, seems like they're getting bigger and bigger. Are you guys considering having smaller rockets for microsatellites, or just in general, just downsizing the size of rockets?
So what we've been trending towards is multiple payloads, either 2 heavy payloads on one mission, or like this, a large payload and many micro satellites, many CubeSats. Yes, we have extra capacity, and as we evolve and actually get our rockets even bigger and more capacity, we'll put double satellites on and go to 2 different orbits, and that's how we'll save there and lower the cost per launch that way. And then still, we'll have extra capacity and be able to launch CubeSats for educational purposes and the like.
Thank you.
All right, we'll come down front here next.
Hi, Peyton Wilson from Wiregrass Ranch High School. I was wondering, just start to finish, like drawing on a scratch board, how long does the whole process of developing the rocket all the way up to launch take?
Design of Atlas V until we first launched in 2002. You know, I think when that started. So I'd say it was, I'm going to go out at probably a 6 to 8 year process by the time when we started the designs on paper and actually had our first launch. So it's evolved expendable. So we evolved the Atlas V from previous Atlas IIs and Atlas Is, and we developed built a new engine on an Atlas II, and then a higher tech Centaur. Increased its capacity. So it started to evolve into an Atlas V until we put a new tank, different avionics, different payload fairing, and where it was an Atlas II is now an Atlas V. And it happened in a step-by-step process. So it's tough to pick out a certain start point, but the starting 6 to 8 years when we first started to when we first launched in 2002. That's it.
All right, we're going to come down front here, and then we're going to go to online questions next.
Hi, Claudette from the Flavor Radio. I wanted to ask you, you said that the rockets drop into the ocean. How environmentally friendly are the rockets? The pieces?
So when they drop in, they're completely, the fuels are completely depleted. So they're empty tanks with an engine that's empty, and it drops in, and they're so far out that it drops down to the bottom of the ocean, and it's very deep where we drop everything off. So, usually breaks up when it hits the water, and it kind of can break up as it's dropping through the atmosphere as well. And the pieces, and they disperse, and you never see them again.
All right, with that, we're going to come to Ask NASA questions. Again, if you're following along online, feel free to shoot us a question using the hashtag AskNASA.
Okay, we have one question on Twitter from Boily35. His question is, what job titles are involved for launch, from planning to launch, so students can help plan their careers and futures in STEM?
Okay, so I'll start with mine. I'm a spacecraft integrator. And in order to be that, I had to work a bunch of different systems on I was a mechanical engineer, so a bunch of different systems on both the booster and the Centaur. And then in payloads too. So I worked up and down the rocket in the mechanical sense. I was a booster propulsion engineer, Centaur propulsion engineer. I was a pneumatic engineer. I was a launcher engineer. I was ground systems at the launch pad. I did all of those things. Sometimes didn't leave one job as I went to the next. I did them both. And so if you can diverse in the mechanical sense, electrically you do that too. You can diversify in many different systems. You can run or integrate the whole system. When you get all of those systems together, you can integrate it together. So.
All right, we've got time for just a couple more questions here. We're going to start down front here and then come over here.
Hi, Debbie Reynolds from Harrison Middle School in Pittsburgh. I was just questioning on are they called solar arrays? Is that what those are called? The solar panels?
Yes.
Could the sickness keep going if they didn't open, or if only one of them opened, or do you have a contingency plan for that?
That is something we've looked at in the past. I believe we determined that we could do most of our mission objectives with some partial deployments. But as you probably noted, it's kind of it looks kind of complex, but it is very lightweight, and it is very innovative from our standpoint. But we've successfully demonstrated deployments over 3 or 4 missions already. But it is still a very critical part of the mission. But yes, we do have contingency plans in place in the event that something doesn't quite deploy all the way like it should.
All right, next question's down front here.
Hi there, Michael Ibel from Cheddar. I know today we've been talking a lot about these rockets breaking up apart upon re-entry. I know SpaceX as well has really started developing reusable rockets that we've already seen last month, the first successful re-entry. I'm wondering where United Launch Alliance is in that process, and if that's becoming a bigger focus as space development continues.
I'm sorry, say that again. You're asking him a question. Go ahead, but you're asking me. Go ahead, I'm sorry.
Rocket reusability.
Right. All right, so for us, right now the Atlas V is completely expendable. And so as we develop other launch vehicles, the Vulcan's coming up, we're going to be able to capture the engines as they're done, as the booster section's done. The engine section will separate off, and we'll catch that and bring that back. The tank, easily made again, and we're going to get the best, most expensive part. We're going to take that engine and bring that back. The other evolving sections, the second stage, we're going to come up. We're going to replace the Centaur with an Aces, and that a much bigger version of a Centaur. So it's not even a Centaur; it's a bigger version, and it will have an extended fuel capacity. It will be able to stay in orbit and be a space tug, so to speak, or be able to get to a point, the midpoint between the Earth and the Moon, be able to ferry things, payloads between the Earth and the Moon, and so we'll be able to reuse those components. So ULA is headed in that direction for reusability.
Interesting, thank you.
All right, last question's going to come from online over here.
Okay, this question comes from Keith SD on Twitter. His question is, what are the reasons for Cygnus' unique solar arrays? Is surface area the only consideration? Does deployment have a high risk of failure?
Good question. If you recall, in some of our earlier missions, we had what we call traditional panel arrays. They were square, and typically what you see on other spacecraft that are flown today. But one of the benefits of the ultraflex arrays is that they're lightweight. So we, in order to increase our performance, get more cargo up for same bang for your buck, if you will, we implemented the use of these arrays. And I think you'll notice, if you look at other future architectures that NASA's investigating and things like that, you'll see these featured in those architectures. So because they're lightweight, yes, there is some risk associated with deployment, but as I mentioned before, we've successfully shown that we can deploy these without issue, and if we don't, we have some contingency plans in place. So that's my answer.
All right, wonderful. With that, we are looking forward to the April 18th launch of the United Launch Alliance Atlas V, carrying the Orbital ATK Cygnus spacecraft to the International Space Station. That's happening at 11:11 a.m. There'll be live coverage on NASATV. For more information about the mission, if you can visit www.nasa.gov/orbitalatk. And as always, join us online when we do live launch coverage on April the 18th. Thank you very much, and have a wonderful day from Kennedy Space Center.
All right. 11:11 would be what? 4:11 tomorrow, I think, BST. If you guys aren't wrong, the golf clap. We're not golf clapping. We're regular clapping. We're regularly clapping. All right. Well, this is the first time we've done that. Thank you guys for participating.
I think there might have been a couple other questions in the room. If we didn't get to them,
there were some questions.
We've got a couple of seconds here to ask a couple of questions.
It's actually,
you want to come up and just talk to some of the experts?
I'm going to mosey over and see if I can figure out. I had a question. Hang on, Jeb, chill out for a second. Jeb's going to hang out for a second. I'm going to walk over here. Yeah, that was different. That was like something that we don't normally do. So that was like behind the scenes sort of. My glasses are so going to fall off right now, I think. Yeah, wait, I got to go ask a question. Time out. Let me see here. Cool. Do you mind if I stream a question for you?
No.
I had a question we didn't quite get to. So you were talking about like the experiments that are coming through reentry.
Yes.
How long do you maintain communication with the spacecraft? Like it breaks up in the end, right? It goes in the ocean. Do you have like telemetry? Do you have information coming back the entire time? Is there like a blackout period, or how does that work?
We are maintaining telemetry.
Right.
We come in and we keep collecting it until it stops.
Until it stops.
Yeah.
So do you have like an expectation for how long that'll be? But it's just we're gonna get data until we don't get data.
Yeah, we keep going, and a lot of times we can kind of tell when certain events occur.
Yeah.
Like a tank will rupture, or
Right.
the arrays break because they stop
Because
collecting power.
it's like, oh, those are gone.
Yeah, so
Nice.
those are kind of interesting pieces of data to see.
Cool,
You
yeah.
can tell if the spacecraft's tumbling or just say one fixed.
Nice. And you're still getting data from different experiments that they can just go until they stop going, basically.
Yep.
Excellent. Good. Thank you very much. I just didn't get a chance to ask it.
All right. Thanks for coming out.
Cool. Thanks. There you go. There's a question. Oh, thanks, dude. You good to go?
That thing is insane.
This thing's not playing around. It goes 6% for 90 minutes.
I can't believe the functionality. Like you have sold me. And
Yeah.
You get a commission.
Look at this. I do actually. Like I do. I'm kidding. It's just on Amazon. Did you get the model number or whatever?
No, but
all right.
I'm gonna find it. And are you streaming right now?
I'm streaming like literally right now. Hi.
We need to share
Hey, what's
stream.
up? Yes.
My name's
hello.
Colin.
It's Colin.
This battery saved my NASA Social experience. It has been amazing. If you want to be a hero at NASA Social, be the person that brings a charger,
Extra batteries.
extra batteries.
Nice.
Be the hero. Thank you. That is
There you
all.
go. If you'd like to support the stream, you can buy this off Amazon. Blah, 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 whatever. We'll get a link to it. No, I literally, chat, I brought two of these. I think they're 28. What are they? No, these are 24,000 milliamp hours. I brought two of these, and I brought my other 20,000 one, and these actually have AC outlets in them. So I just, they have actually AC converters. So I use these to run the wireless internet while I'm going. I have another question. Here's another question. She's playing with VR. Time out. Hang on. We'll ask right quick. I want to see what the deal with the signatures were, because there's some people asking what the signatures on the flight suit were. So we'll ask right quick.
That was a cool view.
Hi. You have signed things on your flight suit.
I know.
What is signed on your flight suit? Look, can we look at it?
This is an astronaut that
Okay.
I met on Friday.
On Friday,
I came
excellent.
with my son.
Okay, cool.
And
the other one?
He works for NASA, and so he wanted to sign it.
Right.
And who am I to say no?
I was just like, okay.
So I'm like, sign mine.
No, I was sitting back here like streaming the whole thing, and the writing on your shoulder was in view like the entire time. And so people were like, "What's it say? What's it say?" We were guessing what it said. Is it an astronaut? Is what it is. So I said I would go and ask right quick to see what
This
the
one's
deal
an
is.
astronaut.
That one there is an astronaut. Who is it?
That I don't
I can't read it.
I can't read it either.
Does anybody recognize that? Like, does anybody see what that is? Anyway,
He was in space for 144 days.
there you go. So collecting signatures on the. Sorry. Oh, we're getting a group shot again. I'm gonna stream the group shot right quick. Let's see here. Hey, and Keith, dude. By the way, good job with the question on the Ask NASA hashtag there. I was trying to get questions from people. Oh, the lighting over here is a little bit rough. Lighting over here is bad. That overhead lighting that makes my hat really stand out. No, the Atraxi, I don't right now. Scrolling through Backpack RTG is nice. Save NASA Social. A calm blackout. That's a good question, Ansem. If I can go catch him, I'll ask him that again right quick. Hey Cole, how's it going? Bam, what's up? Oh, we're taking. Wait. Come out.
Hold on, I'm nervous.
She's taking the picture again. I'm gonna put y'all in the picture. See. It's like once again we're putting picture. Am I blocking you? No. Are we pretty? Okay, good. All right. Okay. Well, y'all, I'm like reading chat and stuff like that. I'm gonna go ahead and shut it down here. Do we have anything else today? I think we do have one more thing. What time is it? 2:30. We've probably got one more thing going on here. I do not know what it is, but I'm gonna go get on the bus, and we're gonna put. Oh, we're going to launch site next. Apparently we're going to launch site. We're not going to the crawler. I thought we were going to go by the crawler, but we might be going out to the launch site fence. So viewers of the stream, you've seen that before. We've actually got to walk around with the United Launch Alliance in the flame trench. We're going to go over there. We're going to be outside the fence. I'll see how the signal is. If the signal is okay, it should be. I'll see if I can just like walk around and do a little bit of thing. But literally, once United Launch Alliance has taken you in the flame trench, watching from outside the fence, it's fantastic. It's good. I mean, I'd rather not see that. But I'm going to shut it down here, and I will be back. It's probably going to be 30 minutes, 45 minutes, something like that. Again, keep following on Twitter. If you're interested in what's going on, if you want notifications when the stream goes live, go to Discord. If somebody can toss links into chat for that sort of stuff. Yeah, nice sunglasses. Thanks. I'm trying to be EJ. I'm trying. Anyways, I am going to go ahead and shut it down before they leave without me. So again, thank y'all for, look at this. We'll go over here. Thank y'all for hanging out with me. Here we go. That's the way to look right there. Out at NASA Social for OA7. That's launching tomorrow at 11:11 Eastern Daylight Time, EDT. It's going to be an Atlas 401 by United Launch Alliance. It's got the Cygnus spacecraft on top from Orbital Attack. And I don't think anybody's going to hear me call them Orbital Attack. But we're going to continue doing this the entire time that I'm out there. So thank you guys very much for hanging out on this new sort of thing that we're doing. I think it's kind of fun because it's like mystery science theater for this sort of stuff with a couple hundred people watching. So good times. We'll do one more stream, I think, today, and going from there. For now, I'm out. We'll see you nerds later.